Welcome to Chapter 10. We're going to talk about the environment and atmosphere, both here on Earth as well as in other planets in the interior of our solar system, here for Chapter 10. So without any further ado, let us get started on this. Let me share my screen so that we can have the right one. Cosmic Perspective, the 9th edition. There we go. And sort of settle in, because this takes a little bit of time to go through along the way. We have an atmosphere. Mars has an atmosphere. Venus has an atmosphere. Mercury and the Moon, not so much. So we'll talk about all of the differences in these places, as well as what difference it makes on the surface of the planets. All of them are called terrestrial planets. Remember, terrestrial means Earth-like. That is sometimes taken with a grain of salt because they're very different from the Earth, but they're closer to what the Earth is like than planets like Saturn or Neptune. So that's why they're terrestrial. Here we have our terrestrial bodies. Mercury and the Moon, as you see, are much smaller. That's part of why they have next to no atmosphere or no atmosphere. Mars, as you see, is sort of mid-sized, and Venus and Earth are roughly the same in terms of their mass and volume. When we're looking at atmosphere, it's a blanket of gas, a layer of gas that surrounds the planet. Sometimes they're much thicker than ours, like Venus. Sometimes they're much thinner than ours, like Mars. Sometimes there's only a trace amount of dust, and that's what we have on Mercury and the Moon. Our atmosphere is 5 to 6 miles thick in terms of breathable atmosphere. That translates into about 10 kilometers, 10K. It is mostly nitrogen and oxygen, something you might be familiar with, and if you've ever gone to the dentist and had laughing gas administered, nitrous oxide. I wrote a science fiction story once upon a time where aliens came to our planet, and instead of taking us over with bombs or lasers or anything like that, they had a device that they could touch the atmosphere and turn all the nitrogen and oxygen into laughing gas. So we just stood there and laughed as they took over everything. Sort of like elections here in the United States. But we have an atmospheric pressure that can be increased in two ways. It can be increased simply by putting more particles into it, like you're blowing up a balloon, or you can heat up the particles that are already there, because as you heat up the particles, they gyrate more, they move more. If they were within a balloon, they would be pushing out more. That's a higher pressure. So you can have two different ways of increasing the pressure in an atmosphere. And we call that here on Earth a barometric pressure, or 1 bar. So barometric pressure is roughly 15 pounds per square inch pushing down on you. So think about how many square inches are on your head, somewhere around, probably around 9 square inches up there, maybe a bit more. Your square inches on your shoulders as well. You've got several hundred pounds pushing down on you. So you're a weightlifter already and didn't know it. That's because even though this much atmosphere and this much atmosphere and this much atmosphere doesn't weigh much, there are particles inside of each of those, and it goes up for miles and miles. So by the time you stack up that many feathers or that many pillows, as you're seeing on the screen here, or that many light things, I mean, what weighs more, a ton of feathers or a ton of iron? Well, the truth is they both weigh the same amount. It's a ton. It's just a ton of feathers will often take much more space. So the atmosphere takes a lot of space, but it does add up over time. Now, just like you have in the diagram here with all of the pillows, the ones that are on top will be less smushed. By the time you've got a ton of pillows, the ones at the bottom are going to be flattened along the way. We have much more pressure down here on our earthly level. And the further down we go, the more pressure there is. If you ever go to sea level versus, say, going to Denver, what's the stadium name in Denver? Mile High. Why is it Mile High Stadium? Because Denver is over 5,000 feet above sea level. There's much less atmosphere. It starts up here. So it might be starting, say, about this level of atmosphere rather than this level of atmosphere. That's why sometimes if you drive up to the Rocky Mountains, or if you're a sort of a marathoner and you go to the marathon race at Denver, but you've been training here in Indiana, or you've been training, say, on the beaches of Florida, you might be out of breath before too long because there's not as much air in the atmosphere there. Literally, there's not as much air that's in the atmosphere there. Now, this pressure is different on Mars. This pressure is different on Venus. This pressure is unique to the Earth along the way. There's no clear upper boundary. People tend to think about 50 to 60 miles up. Again, 100 kilometers translates into roughly 60 miles, would be where we would consider space to begin. That's where the sky stops being blue, the light stops scattering, and we'll talk about this in a moment, in the atmosphere, and it turns dark along the way. But you're going to get particles hundreds of miles up into space all the way. Here we can see, so this is the old space shuttle, which isn't operating anymore, but quite frequently it would go 100 to 200 miles above the surface. That tended to be one of the mission zones that it would be. So here we're going to have it roughly 180 miles up or so. And you can see it's still actually impacting a little bit, tiny amounts of atmosphere. Not nearly enough to breathe, not nearly enough to keep your body from exploding. Believe it or not, the atmospheric pressure helps keep us together along the way. But atmospheres create the pressure that keep us together, also keep water together. If you don't have atmospheric pressure, it doesn't matter what temperature it is. You're not going to have liquid water there. You have to have the right kind of environment, and atmosphere provides that. That's why it doesn't always matter what temperature it is on Mars. You can actually have what we would consider temperature-wise to be 40, 50, 60-degree day. Believe it or not, that sometimes happens there, but there's not enough atmosphere to keep the heat in, so it's not going to feel that way to your body, and it's not going to allow water. Atmospheres absorb and scatter light. When they absorb light, they sort of take on the heat. They create our climate, wind and weather. They create a solar wind with the magnetosphere. That's what you were seeing in the picture before there. That's the Aurora, which I believe we've talked about a little bit before. We'll talk about it again here from up above. And it creates a greenhouse effect. Now, greenhouse effects are good. We want a greenhouse effect. The moon does not have one, which is why it goes from boiling to freezing every single day. We don't want a runaway greenhouse effect. Keep that distinction in mind, and we'll talk about it later. What happens when we have a greenhouse effect is the light comes through, heats up our surface. As the surface re-radiates out the heat, it gets bounced around by particles. The more particles, the more bouncing around it is, so the more cumulative heat you're going to have in your atmosphere there. That's why more particles means more heat. That's why we pay attention to how much carbon and other things are in our atmosphere along the way. Visible light, Roy G. Biv, passes through, but infrared will tend to get trapped. Venus has a runaway greenhouse effect because it has a lot more particles than we do. Mars doesn't keep itself very warm because it has so few particles, it doesn't trap the heat anymore. So greenhouse effect is a good thing in moderation, but sort of like the Goldilocks idea. If we're too hot, we're too cold, that's not good, but just right. We don't want to be too close to the sun. We don't want to be too far away from the sun. We don't want to be too much atmosphere with particles, and we don't want to be too little atmosphere with particles. So we are in the temperature sweet spot. We're in the Goldilocks spot. Now, planetary temperatures will be determined by a lot of different things. One is how much sunlight it's getting versus how much heat it can radiate back out. Also, how close it is to the sun can make a difference. That's not always the critical difference, though. Venus is hotter than Mercury, even though Mercury is closer, because Venus has the atmosphere to absorb and retain the heat that Mercury does not. The rotation effect has one side absorbing the heat while the other side is radiating it back out. So that will affect the temperature differences as well. When you are on Mercury again, in the hot day, you're over 700 degrees Fahrenheit, 420 degrees Celsius. When you're at night, you're minus 170 degrees Celsius. That's a huge drop of temperature. We're talking like minus 300 or more. So you have literally 1,000 degrees difference Fahrenheit between day and night on Mercury. It rotates very slowly along the way. If it rotated much faster, that temperature might be a little bit, temperature variation might be a little bit different. On Venus, day and night, not so different, because the atmosphere holds the heat in. So day and night, it's 470 degrees Celsius. So that's putting it over 800, closing in on 900 degrees Fahrenheit, day and night. Also the reflectivity. If you're reflecting a lot of sunlight back off your planet, especially before it gets absorbed into the planet, you're not going to heat up as much. So if we have more ice, if we have more snow, if we have more clouds, we have a higher albedo, we reflect more light, we don't warm up as fast. Ironically, Venus has a very high albedo. It reflects back 75% of the light it gets from the sun. That's why it turns out to be so bright in the night sky or in the morning sky. But the 25% it does absorb, it never lets go, it seems. And that's why it's so hot. It's there. If we had no greenhouse effect at all here on Earth, notice our average temperature would be well below freezing. Remember, Celsius, the temperature at which water freezes is 0 in the Celsius span. So we're going to be below freezing with no greenhouse effect, whereas our average actual temperature is well above that. Notice 15 degrees Celsius isn't that warm, but we're taking an average here, so you're averaging where my penguins are as well as where we are here in the summer in Indiana, where it's really hot along the way. Notice again our temperatures on Mercury night and day. Notice our moon temperatures night and day. Notice this here, the night, it's the same. When you're not getting sunlight, you're not getting sunlight. That's just how cold it is. But the daytime, why is this different? Aha, Mercury is much closer to the sun than the moon. So Mercury gets a lot more sunlight than the moon. There's no greenhouse effect. There's no averaging greenhouse on the moon or on Mars or on Mercury. There's barely one on Mars. There's a lot on Venus. There's a moderate amount on Earth. Again, we're sort of in the middle there. We're in our sweet spot there. So Venus would be a lot colder. If it didn't have a greenhouse effect, we would be somewhat colder, but we would be below freezing on average, so that would not be a good thing for us. Atmospheric properties vary depending upon how high up you go, and how high up you go will change two different things. One, how much sunlight is getting through, because some of it gets blocked before it gets all the way down, as well as how many particles are up there. There are 4 different ways that light works on the atmosphere. Ionization, as a light particle comes and hits a particular atom or molecule, it will strip off an electron. That's called ionization. Dissociation is when it comes through and disrupts the molecule altogether. So if you've got H2O and it hits it, it might separate an H. So you'll have a free H floating around, and then you'll have an OH over here floating around. It also gets scattered. The light can get scattered, especially if we have water vapor, because water vapor will quite frequently, especially if we've got water droplets, and that can really change things into a rainbow. It scatters things quite a bit. And then we have absorption. Sometimes the photon is absorbed into the package and it sort of energizes it, it heats it up. So those are the 4 ways things happen. X-rays and UV light, which are very high energy portions of the sunlight. If you remember back when we were talking about our electromagnetic spectrum, these will do the ionization and dissociation. These are what split things apart. Molecules, denser molecules, sort of O2, usually oxygen isn't just floating around by itself, it's in pairs, so O2. Nitrogen is also usually in pairs into Water vapor is H2O, so that's 3 particles together. Those molecules will tend to scatter things. Blue is more energetic than red, so it scatters more easily, hence blue skies. Molecules can also absorb the infrared light. If you think about infrared lamps at buffets and such like that, that heats us up. In the troposphere, notice the word here, tropic, is the base word for that. We are at the lowest level. That's where we live. We live in the troposphere. This is sort of the first sort of 5, 6, 7 miles of it, so our main atmosphere. By the time you get above the troposphere, you can't really breathe. There's not enough air up there. And the tops of the highest mountains, like Mount Everest, are just on the borderline of the top of the troposphere. Notice our temperature goes down as we go up into the troposphere. There are fewer and fewer particles to hold the temperature. Also, the heat bubbles from the infrared are sort of dissipating. The heat rises, but it's dissipating into this less and less and less particles that are there along the way. So we're closer to the warm surface if we're down near sea level. So it gets colder. Even if the mountain is on the equator, like Mount Kilimanjaro is right near the equator, it still is going to have snow-capped peaks because of that. The stratosphere is our next layer. Notice how high that goes up. So that goes up sort of another 20, 30, 40 miles that's there. You can see this is in kilometers here. So we're thinking about like 20, 30, 40 miles by the time we get up to here. Maybe a little bit more than that. Notice we've got this block here. We've got this stratospheric area where our UV rays are getting blocked. This is where our ozone layer is. Ozone is 3 particles of oxygen, three atoms of oxygen that are together into 1 particle. And when UV light hits it, it will, again, break it apart, dissociate. But that also blocks the UV from making it all the way down to the surface. Take away that layer, and we take away our protection along the way. Notice the temperature goes back up here because that's the area where it's happening. So as that action happens, it heats up. But there are so few particles there, you would still freeze, because even though each particle is more energetic, there aren't enough of them to keep you warm. And then above that, we have the thermosphere. Notice where temperature goes back down until we have a spike up again. That's where the X-rays are energizing the particles. But again, by this point, we're almost at vacuum layer level of particles. There's almost nothing here anymore. Very, very few. And when I say very few, I mean we've got 1 billion more particles down here than we have here per any given area along the way. And then the exosphere, this is where just energized particles will escape and float away. We do actually leak atmosphere, because if there's a particle that's up there that gets hit by something that energizes it, it might give it enough energy to overcome the gravity of the Earth. It's not a fast process. We're not going to run out of oxygen or atmosphere anytime soon. But notice we've got this little break here. We go from 100 kilometers to 500 kilometers. So the exosphere goes way, way, way up. Nowhere near the moon. Or not anywhere close to the moon. If this was the Earth, my hand was the Earth, and this was the moon, the amount of atmosphere on the Earth would not even be the sort of the outer skin layer of my hand. So the exosphere does not extend out to the moon by any means whatsoever. But as I mentioned before, the sky is blue, because blue is more energetic and gets scattered more. So if I go outside right now, the sun is up. That's why you're sort of seeing sunshine on one side of my face and not on the other. I would look up, and if it's not cloudy, I would see a blue sky. Except if I go out at sunrise or sunset, what color is the sky? Well, you get reds and yellow and orange and other kinds of things in there. That's because all the blue has scattered away. The light is actually coming through more atmosphere at this angle when you're at sunrise or sunset than it is when you're looking at it at noon. If I'm looking at the sun at noon, it's going through about this much atmosphere. But if I'm looking at it at sunrise, or if I'm looking at it at sunset, it's going through a lot more atmosphere, maybe 3 times as much atmosphere. All the blue has scattered away. And what's left over is the ROI. The BIV part is gone. That's why the sky is blue. The atmosphere of other planets are a little more simple than ours. Mars has a sort of, as you can see, as you go up above the surface, it gets colder, but it levels off. Venus also, as you go above the surface, it gets cooler, but it's hot, 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 all the way up to what we would consider to be its boundary of space until it gets really out of its sort of atmospheric area, because it has such a thicker atmosphere along the way. So this is quite a dramatic thing along the way. We are the only planet that has an ozone layer, and that's interesting. Mars may have had an ozone layer in the past when it had a more substantial atmosphere. As I mentioned, our atmosphere is leaking a bit. Mars is actually leaking a lot more. And once upon a time, it probably had a thing shut off that kept it with an atmosphere, and that is the magnetic field. That's what we have on the screen right now. We have a magnetic field that's generated from inside. We talked a little bit about this when we're talking about the geology of our planet. We have the sort of sloshing around of iron in our inner and outer core that generates a magnetic field that keeps the solar wind particles. The sun is sort of breezing off things. It's like a very fine sandpaper kind of thing that gets caught in our atmosphere. We see the northern lights. That's where that comes from. But if this shuts off, if this magnetic field were to shut off, that sandpaper effect would scrape off more of the atmosphere, and over billions of years would wear it away much, much, much faster. Well, guess what happened to Mars? Mars lost its magnetic field. So over time, even though Mars is further away from the sun, it's still getting solar particles. It's still getting that sort of sandpaper brushing, and it's helped to wear away the atmosphere. That's not the only effect, that's not the only cause, but that's one of the major causes. Why did Mars lose its magnetic field? Glad you asked. Well, remember that picture we had a couple of slides ago, well, more than a couple of slides ago. There we go. Notice again the size. The smaller you are, the faster you cool off. We talked about that in an earlier lecture too. It cooled off, which means its iron stuff in the middle solidified. It's not sloshing around anymore, so it doesn't have a magnetic field the way that we do. So poor Mars, no Aurora Borealis for them, not really. But you can see things like this. This is from Canada. We also have them in Iceland, where I go quite a bit. We also have them in Alaska. You can even see them in the Upper Peninsula of Michigan on a regular basis, northern Minnesota, up in Maine quite frequently. Every now and then you can actually see them from central Indiana and central Ohio. But city lights and light pollution will really kill your ability to see the aurora along the way. So these are the things we've learned. I'll let you look at that on your own along the way. We live in a weather-dominated environment. What creates this? Well, as we are spinning, it's not as simple as the wind is being left behind, because we have different weather patterns depending upon where we are on the planet. Our equatorial winds go from east to west, but here in our mid-latitudes, things tend to go from west to east. If you watch the Weather Channel, as I do, you often see most of the weather of the United States coming from the west and going to the east. On the other hand, if you watch the hurricanes and other kinds of things that are coming off of the Atlantic, they're going from east to west. They're in a different area. And then when they skirt up into the United States or up into the Caribbean or other areas like that, they begin to fumble and change directions because the general weather pattern changes. Then when we get back up to the polar region, or down below, down to the polar region, we're going east to west again. So we have a complex system on our planet. Now, weather is what happens today and tomorrow and this weekend. Can you go for a picnic? Climate is the long-term average. Should I plant crops here? Do I need more insulation? Do I need a advanced kind of air conditioning system along the way. One of the things that really upsets me is when people who are trying to deny climate change like to stand out in the middle of the winter and say, where did global warming go? They're confusing weather with climate. And I immediately turn them off and I go in and I block their pages on Facebook and all of that stuff because they're not being intelligent about it. What happens, of course, is none of them are ever saying anything about where did global warming go when I go outside and it's 110 degrees in June. So, well, here you go. Here's global warming. Actually, that's not actually global warming either. That's still weather. We'll talk about climate change here in a moment because guess what? The climate's changing. Guess what? For 4.5 billion years on our planet, the climate has been changing. It never stays the same. And there are lots of reasons for that. But as we have a complex system in our world, we have different weather patterns that form along the way. And a lot of that is due to the unequal heating of the Earth. We get more heat around the equatorial ranges, in the tropics, the tropical area. We get less in the mid zones where we live and sort of middle of South America and middle of Southern Africa. And then we get the least amount in terms of intensity at the polar regions. Even though you might have 24 hours of daylight at the poles, you're getting less intense heat there, less intense light there. So it stays cold even in the summertime there. What we have are circulation cells. Of course, the hot air will tend to rise, the cool air will tend to drop. So if we weren't rotating, this would be how things would be going. The hot air from the equator, the equatorial region, would be going up, and the cold areas from the Arctic and Antarctic would be going down, and it would create these cells. But because we are, in fact, rotating as a planet, we get the Coriolis effect. And you may have all seen the Simpsons episode where Homer Simpson goes to Australia and he asks, is it true that the toilets flush in the opposite direction in Australia than they do in the United States? And the guy in the embassy there says, it's true, but we've installed a special device that puts it in the right direction so you can feel at home while you pee. Now, here's the thing. That's not actually true. Here's what is true. The spin of your drain, whether it's bathtub or toilet or sink or swimming pool or whatever, has more to do with the plumbing system and the elevations and other kinds of physical attributes of what's putting the water there in the first place than it does to the spin of the Earth. So when we're talking about the rotation of a drain, that's not true. When it comes to weather patterns, however, it is true. The northern hemisphere and the southern hemisphere rotate in opposite directions. That is called the Coriolis effect. And you can actually notice that if you're on a merry-go-round or something like that, and you try to roll a ball, and roll the ball, it'll go in the opposite direction of the spin of the merry-go-round. That's because as we are spinning, see, the water is actually grounded, but the air is not grounded. So when we're looking at things in the northern hemisphere, things will tend to go counterclockwise because it's going opposite the spin. In the southern hemisphere, things will go clockwise because, again, it's going opposite the spin. If you think about clockwise versus counterclockwise, and the screen is reversed for me, so I don't know which you're seeing when I'm doing counterclockwise or clockwise, but if I do this here, to me, on this side, it looks like I'm going clockwise. But if I were looking at it from over here, it would look like I'm going the opposite direction. If I'm looking at it this way, or if I'm looking at it this way, it looks like it's going in the opposite direction. If you're standing at the North Pole and watching the stars go around the pole star, or if you're standing at the South Pole and watching the stars go around the South Pole, the South Celestial Pole down there, they go in opposite directions. And that's because the Earth is curved. Guess what? The Earth is curved. It's not flat. And that's one of the ways you can tell. So north is counterclockwise, south is clockwise in terms of the storm cells that happen along the way. The way I remember this is counterclockwise has an in it. So the north is counterclockwise. We can't use the S because it's in both of them, but there is no in the south, there is no in clockwise. So that's how I remember that. So if you happen to have a hurricane down in the southern hemisphere, usually they're called sort of typhoons or other, but they use other terminology for them typically. But if you had one in the southern hemisphere, it would be going in a clockwise direction. If you have one in the northern hemisphere, which is what they're usually coming up to hit Florida and Texas and other places like that, they're going in a counterclockwise direction. When we have that happening along with our rotation, what we get are these different kinds of cells, and they circulate amongst themselves with only a little bit of overlap here and there. So most of the cooler air stays around the Arctic regions. Most of the hotter air stays in the tropical regions. And we, again, are in the Goldilocks zones here with our different temperatures along the way. And that's partly how we develop our prevailing winds. Most winds go in the United States from west to east. Most winds go in the tropical zone from east to west. Then we have, as part of all of this, as if that's not enough that's going on, the water cycle that happens. And the water cycle is something that's been known for a very long time. Water evaporates, it seeds the atmosphere, it condenses into clouds, the clouds grow, and then they return the water to the surface through rain or snow or hail or other kinds of things along the way. But that's all collectively called precipitation. This has been known for a very long time. If you go to a book called the Bible, go to a book in that called Ecclesiastes, you will see that they have a description of the water cycle. That book was written about 3,000 years ago. So they sort of knew what was happening back then in terms of how water gets recycled, how the climate changes along the way. Because climate does change, and there are several reasons for that along the way. For one thing, the sun is getting brighter. That is true. And you will sometimes hear these radio commentators that I mentioned before saying, well, of course we're getting hotter, the sun is brightening. Well, here's the thing. Usually they will say that the day after they've just denied the climate is changing, so they don't even listen to their own thing. But don't get me started on that. But here's the thing. The sun is brightening, which means Mercury is getting hotter, Venus is getting hotter, the moon is getting hotter, Mars is getting hotter. But here's the Earth. Whoops, we're getting hotter than we should due to solar brightening. Solar brightening is just teeny, 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 tiny amount. Solar brightening would be like if I were trying to start a fire. You know, one of the ways you can start a fire is sort of rubbing sticks together and getting the heat from the friction to start a fire, and you need dry leaves and all of that sort of Boy Scout survival kind of stuff. Well, solar brightening is kind of like, would I ever start a fire just rubbing my hands together like this? No, I would not. That's about as much. In fact, I'm probably generating more heat than we're going to get from solar brightening in any given 100-year period. So even as the sun does brighten, it's a very, very, very slow process. So it's a very minor thing. In the long term, it makes a difference. When I'm talking long term here, I'm talking millions of years, not hundreds, not thousands. Another thing is our axis tilt. And we've talked about this before. We have seasons because we are tilted. And sometimes we're tilted towards the sun. Sometimes we're tilted away from the sun. And when we're tilted away from the sun, like in this picture here, the north is tilted away from the sun, the south is tilted towards the sun. So seasons are opposite. Well, here's the thing. If we're tilted even more, there's going to be more of an extreme between the seasons. If we're tilted less, there will be less of an extreme. So one of the things that happens there is our tilt is 23.5 degrees, but sometimes we're all the way over to 25, and sometimes we're back up to 22. We wobble just a bit. that will change things along the way. As I mentioned, we're right in the mid zone for that right now. That wobble also takes tens of thousands, if not hundreds of thousands of years. So this is a very slow process also. Then we have changes in reflectivity. When we have more ice and snow, we beam more heat back into space. When we have less ice and snow, we absorb more of it. When we have more blanket stuff in the sky, like a volcano erupts and it blankets the sky with lots of clouds, that will reflect more stuff and will cool off. When we have less particles obscuring the sunlight, we will in fact heat up. Those things happen on a regular basis on the Earth, but they happen more randomly. They're not as regular. We can't really predict when climate changing volcanoes are going to take place. Although we have had some. There was one volcano that was traced to Iceland that erupted one year, and the next year there were so many particles in the air over the northern United States that it was snowing in July. It was keeping that much of the sunlight away from us. So yes, climate change happens in a lot of different ways. What the main concern is today, what people on those radio shows and talk shows and other things are talking about, what Al Gore talks about, what scientists talk about, what politicians talk about, are changes in the greenhouse gases. Are we making things worse? Are we making things better? Are we doing something that helps or hurts along the way? It is true, the more particles you have, the hotter things are going to get. That's true on Venus, that's true on Mars, that's true on the Earth as well. So, do we have more particles, yes or no? The question is, in terms of our entire atmosphere, we do actually lose a few particles, but we have an ongoing recycling process also that happens. We get more gases into our atmosphere when volcanoes erupt. It takes a while for some of that dust to settle, but there's a lot of oxygen that gets leached into the soil. It's oxidation, it's rust. We get a lot of oxidation that happens all over the world. We get a lot of stuff that's leached into our planetary sort of physical body. But when we get little particles that hit, we can actually have some of that erupt and go back into the atmosphere. When we have, of course, vaporization, anything that is sort of evaporated. So, you can take a solid and then melt it, and you can then take a liquid and then you can evaporate it. You can add energy to it, you can add heat to it. And most things will operate that way. Of course, most things will then condense back into solid fairly quickly, but this is an ongoing process. Guess what? For Mars, when it cooled off, not only did it lose its magnetic field, it also lost its volcanoes. So one of the parts of putting things back into the atmosphere shut down there. So it had a double whammy. You can lose gases, again, by oxidation. You can lose gases by things condensing onto the surface. That's either liquid or solid. So water vapor leaves the atmosphere by either raining or by freezing and becoming ice and snow along the way. We also get a little bit of escapage at the top. Mars gets more than we do. We have more gravity than Mars does along the way. There is a calculation for that. Every planet can have some of this escape stuff along the way. We don't actually lose very, very much, as you can see from this. I'm not going to make you do the math, don't worry, but there is math to support this, just so you know. As I mentioned before, Mercury and the Moon, not so much in terms of its atmosphere. We really only talk about it as having an exosphere, it doesn't have a troposphere, doesn't have a stratosphere, doesn't have a thermosphere, doesn't have any of those things. But it does have a little bit of dustiness around. It's just the gas that comes from anything that hits it and kicks up the dust. And eventually most of the dust will settle back down. Notice the difference between these two though. Moon over here, Mercury here. Why is Mercury so much sort of shattered and scattered? The Moon looks like it's just sort of drifting there in its sort of haze. That's because Mercury being so close to the sun, instead of getting a gentle kind of sandpapering from the solar wind, is actually getting quite a bit. So that makes a difference there. But there's really no effective atmosphere. Some of the gases that in fact escape, though, are things like ice. As I mentioned before, at night it's minus 175 degrees Celsius on the moon and on Mercury. There's some areas that stay permanently in shadow, and because there is no other atmosphere to carry the heat over from here to here, it stays in shadow. It stays that cold in those portions where it's always in shadow. So some things stay pretty icy. But if it edges just a little bit, if there's a little bit of an impact, a little bit of a tremor, a little bit of something that edges some of that ice into the sunlight, it's going to, in the heat, whether it's the 420 degree heat of Mercury or the 120 degree heat, and again, we're talking Celsius here, on the moon. Either one, that's hot, hot stuff, and that will evaporate stuff. So on Mars, we do have an atmosphere, but it's only about 1% of what we have here on Earth. But that's enough to give us some quite dramatic displays. Here we can see a worldwide dust storm that happened in 2018. This is one of the dangers of planning to go to Mars, is these are not very predictable when this happens and when it doesn't happen along the way. Mars has seasons because it has a tilt that is like ours, but Mars actually extends further away from the sun at certain points than we do. We're almost a perfect circle. Mars is less of a perfect circle. It's still pretty circular, but it still gets a little bit further away than we do. And when that happens, that means it gets less sunlight overall, which means its seasons can be more extreme, especially in its southern hemisphere. It has a north and a south as well. Now, Mars also wobbles a lot more than we do, because it's not sloshing around inside the way we are. It's actually solidified, and probably solidified not completely spherically. So it's sort of, if you've ever seen the Weebles kind of toy, it sort of wobbles around quite a bit. Mars wobbles quite a bit more than we do. One of the things that we can see to track the seasons there is we have ice caps. We have polar ice caps that grow and shrink on Earth. They grow and shrink on Mars as well. Part of this is carbon dioxide, and part of it is water ice, H2O, that's there. You can have water as ice on the surface, but liquid doesn't tend to last. You don't need the atmospheric pressure to keep ice solid. You do need the atmospheric pressure to keep water liquid. But we have found different kinds of water, H2O, most likely even some liquid, but a lot of frozen water, in different kind of icy areas and dusty areas. So it is possible that there might be some residual, very, very deep volcanic heat that can keep the water liquid below the surface, where the atmospheric pressure doesn't matter as much along the way. We do see dust storms. These little things here are all tracks from dust devils that have sort of gone off in all sorts of different directions here. And here we see a dust devil in action, a sort of a little miniature tornado that's whipping through here. So it's a really active place. Although if you've ever seen the movie The Martian with Matt Damon, at the beginning of the movie, it's sort of the one big mistake in terms of science. And the one big mistake is they're all running for this rocket to take off because the wind is battering it. So let's say this is the rocket and it's there and the wind is battering it and it's going to tip over and it's going to have a problem. There's not enough atmospheric pressure on Mars for that to happen. It would be as if I were to go up to the rocket and go, it's enough to kick up dust everywhere, but it's not enough to really whip anything around. So that's the one downside there. On the other hand, it can obscure the light. So if you're going to the Martian surface with solar panels, that can actually kill a lot of your problems, or a lot of your power there. Here's what I was talking about before in terms of the magnetic field when it had a molten core that was sloshing around. When the molten core shut off, So did the magnetic field. Also, when the molten core shut off, the volcanoes that you can sort of see here shut off. And a lot of the things that were being put back into the atmosphere of Mars just got leached into the soil and stayed there. As the gases were lost to space, the solar wind hitting Mars, brushing things off. There's less gravity on Mars to hold on to things. There's now no magnetic field. There's now no volcanic activity and outgassing activity to put things back into the atmosphere. It just slowly dissipated, so that now we're only about 1% of what the Earth has. Mars may have had a thicker atmosphere than we have once upon a time. It may have had enough to have liquid oceans on the surface. We've talked about that before. The axis tilt, as I mentioned, we go from 24 or 22 to 25. We're at 23.5 to 24 right now. Mars goes from 0 to 60. So yeah, it's like that's going to have quite a bit of an impact on climate changes along the way. So Mars's climate change, again, because everything shut off the way it did, probably about 3 billion years ago. So it was about 1.5 billion years old. It lost its atmosphere, it lost its particles, it lost its volcanoes. It lost most of the greenhouse effect that it needed to keep the surface warmer. And therefore, it became a problem planet. It lost a lot. We don't know what might have been there before. We don't know if it might have developed life and an ecosystem. It took a while for major life to happen on our planet, so we're not really that convinced that Mars would have developed like civilizations and such like that in the time. But it could have been, could have had plant, could have had maybe even very sort of rudimentary, what we might consider animal life. It certainly had time for bacteria and other kinds of life of that sort. Anything that we can find on Mars will give us an idea of what life is like in terms of its processing into how things develop. And that would let us know what happens on other planets outside of our solar system as well. But size makes a difference here, because if you can't hold on to your atmosphere, you don't have enough gravity because you're smaller. You can't keep your core molten because you're smaller. So you can't keep your magnetic field and you can't keep your volcanoes because you're smaller. Then you're sort of doomed. And that becomes an issue. So talked about this here already. Venus is about the same size as we are, again, in terms of volume as well as in terms of mass, the stuff that's in there. It is much denser atmosphere than we have, 90 times that of the Earth. So if you think about those 15 pounds per square inch pushing down on you, multiply that by 90 and you can't ever get out of bed in the morning on Venus. Not that you would anyway, because there's sulfuric acid in there. So it would probably eat you away if it didn't just crush you or melt you in the excessive heat. Because Venus, remember, Venus is the planet that goes around the sun in 225 days, but only spins on its axis once every 245 days, and it's spinning upside down. That means it doesn't have that rotation that we have, so it doesn't get the Coriolis effect, and that doesn't affect the weather that's there. It's very, very thick carbon dioxide. That's one of the key greenhouse gases that we watch on our planet. Why? Because we can see what it does on Venus. And it creates this huge, huge problem there. Now, most of our carbon and oxygen and other kinds of things like that will be in our water and rocks and oceans and other kinds of things. Most of the oxygen on our planet is actually not in the atmosphere. But we don't have a recycling process on Venus the way we have on the Earth. So Venus got very, very hot, in part because it has as thick of an atmosphere as it does. What light gets through, it reflects, again, 75% of the light that hits it from the sun, but the light that does get through is trapped by this enormous amount of particles. That's 90 times denser atmosphere that we have that's there. We don't know as much as we'd like to about the processes that govern the atmosphere. We're still working on the fast winds that are at the top. But this is the runaway greenhouse effect. We're not in any danger of turning into Venus anytime soon. But if you don't have a process where carbon dioxide is taken out of the atmosphere, it heats up and heats up and heats up along the way. So if we were to lose our oceans altogether, we could end up being like this. We're not in any danger of that anytime soon along the way. So if it had a runaway greenhouse effect, it's possible that Venus, like Mars, like Earth, may have had oceans once upon a time, but there might have been chemical processes that kept it from recycling the CO2 the way we do here on our planet along the way. So it is sort of interesting that Venus and the Earth are so similar and yet so different along the way. Our atmosphere being different, we have 4 key questions. How did we retain the water when others didn't? Why do we have so little carbon dioxide like Venus? Why do we have mostly nitrogen and some oxygen? Why do we have our ozone layer? Well, we're cool enough to allow liquid oceans to form, but not so cold that they will, in fact, freeze. That helps with the CO2 along the way. We have a lot of rock kind of leaching out of stuff in the atmosphere, but what is going to leach out is mostly going to be things like the oxygen. So it's going to leave the nitrogen behind. We have plants that put oxygen back into the atmosphere. That's a relatively new process on our planet. For the first couple of billion years, that was not a thing. Then we also have our ozone layer here, which allows for O2 and free O's to sort of form together. So plants releasing the O2 help this process along the way. So we have this sort of ongoing process. Our climate is pretty stable because things are in balance. Throw things off balance and things become a problem. We not only have the water cycle, we have the CO2 cycle. Carbon dioxide actually dissolves in rainwater. It erodes into the minerals, and the minerals combine with the oceanic floor to get pushed down into our magma. And then the magma comes up back into the volcanic activity and puts stuff back into the atmosphere. So not only do we have that water cycle, we have the CO2 cycle. That was not mentioned in Ecclesiastes, by the way. But what happens is we have ups and downs. Our climate is always changing. This is, again, if people say, well, I don't believe in climate change. Our climate is always changing. It's going back and forth between hot and cold. When we have more CO2, more carbon dioxide in the atmosphere, one of the things that happens is we'll start to heat up. When we heat up, we have more precipitation, more water vapor, because you can have more humidity in hotter atmospheres. One of the things that's going to happen is we're going to have the CO2 process again kick in, and we're going to have more of it decreasing out of the atmosphere and into our processes with rainwater and minerals, because there's more precipitation, which is going to cool us down. And then when we cool down, we have less precipitation and it all starts up again. So we bounce back and forth. We have warming trends, we have ice ages, back and forth. And we've had several of those in human history. They've been minor, they haven't been major. We've had no major ice age, but we had the miniature ice age during the Viking era, the late Viking era. We had the medieval warming spell in the early Viking era. We've had different warming spells and cooling trends that have caused actually whole human civilizations to shift the way they do things along the way. And I'm going to try and find a documentary called The Little Ice Age. I have it on a disc in my closet. That does us no good in the virtual environment, but I think it's available online. So I'm going to write myself a note here to remember to post that up here. Little Ice Age video. And there was a really good documentary on the History Channel on that. that talks about how the climate shifted from its earlier warm period where lots of things would grow in abundance in a lot of environments, especially in Europe, that then all shut off and people were like, oh, what's happening? Well, we've had ice ages here in North America as well. Are any of you from Martinsville? I may have mentioned this before. The last ice age stopped just around Martinsville, the glacier expanse of that. Of course, the rest of the planet was cooler, especially the rest of the northern hemisphere was cooler when that happened along the way. But we have these things happen, and that was not millions of years ago. That was like 10, 12, 15,000 years ago along the way. We have had periods where we've had expansive ice ages. We've had periods where we've had such warming trends that we've had no polar ice caps. We've had at least one period, maybe more than one, where the entire surface of the Earth was covered with ice. Now, water freezes on the top, which means the oceans were still liquid underneath and we still had heat from volcanoes and other kinds of things. This was called snowball Earth here. But this has been happening for billions of years. And part of what happens here is also the way the continents shift around. When they're all shifted together versus all spread apart, that creates new networks of heat and cooling transfers through the oceans along the way. So we have this change. I may look for, I'm going to write another note to myself here while I'm thinking about it, a documentary called Snowball Earth, because there are a couple of those that might also be worthwhile. So you can see what happened to the Earth in its really cool times along the way. So the key question among politicos, among industrialists, among talk show hosts, among academics, among scientists, among people in general is, are we in fact heating up the planet? The truth is we are putting more particles into the atmosphere. That is not under debate. That is something that we do. And the question is, are we doing it enough to damage things? Well, we have done things to damage our atmosphere significantly. The ozone layer. When I was a kid, and this is only 50 years ago, my mother would take me out to the beach in Florida and she would put suntan accelerant on me because I'm, as you can see, pale guy, and I would need that. Well, if you did that today, you could probably accuse my mother of child abuse because we go out today and we put skin factor protection 10,000 on. Part of the reason why we have a shift in just 50 years of that are something called chlorofluorocarbons, CFCs. And chlorofluorocarbons were found largely in hairspray, in spray paint, and largely in air conditioners and other industrial products. These particles would float up. We had no idea when we were making them that they did this, but they would float up and they would attack the ozone layer from the underside. So while the ozone layer was being hit from the top by regular UV rays, it was also being hit from underneath by our stuff that we were making. People recognize this. All over the world, people recognize this. Every country in the world recognized this effectively. And we stopped making these things and we shifted and adapted so many different things around so that we weren't damaging the ozone layer anymore. And when we shifted that, the ozone layer started to regenerate. So we're not in any danger anymore of just having relentless UV rays hitting us, because that's not good. That can damage your retina and that can cause skin cancer. So we have affected our atmosphere and we have affected things on our planet, and we know this already. As we look at the way temperatures shift along the way, we can see the average temperatures on our planet have gone up. Now notice over here on the left-hand side, this is 1 degree Celsius. So we're not talking about it getting 10, 20, 30, 40 degrees hotter. So if anyone's talking about that, they're being an alarmist. But a ½ degree increase in 50 years is significant. And the trend is also significant. Are we doing anything to bring it back down? Are we doing anything to level off? Because if we keep going on that pattern, That's not going to be a healthy thing for us. We can see over the last 50 years that our concentration of carbon dioxide has gone up and up and up and up. And we are now above 400 parts per million here. Whereas 50 years ago, we were at 300 parts per million. That's got to make a difference. How much of a difference? That's part of the continuing debate. Now, here's one of the things that is interesting. As we look at the temperatures on our planet, we can measure that from tree rings, we can measure that from soil samples, we can measure that from ice cores in the Antarctic, we can measure it in a lot of different overlapping ways that confirm each other. We can also test the atmosphere from those times because there are air bubbles that get trapped in those ice cores, and there are air pockets that get trapped in different ways. We can tell whenever there was an increase in carbon dioxide particles, there was an increase in overall heat in the planet. Well, we're up above anything we've seen for at least 1 million years. So we're in for a warming spell along the way. One of the things that tells us, however, as we're looking at the long-range trend, is the long-range trend tells us we might have been in a cooling pattern. We actually might still be in the leftover of the last ice age, because as I mentioned, it was only like 10, 12, 15,000 years ago along the way. When we're talking about things that are 1 million years long, like that other chart, that's actually not that far away. We may have been on a natural cooling trend as we're putting things in to make it warmer. So we may have actually been saved from our own problems by the fact that we're going counter-cycling along the way. But some of the consequences of global warming, when they go out and it's 40 below zero in the middle of Manhattan, and it's never 40 below zero, although the wind chill can kick up that. They say, where's global warming? Well, here's the thing. That is global warming. Because what global warming will do is it will make the intensity change. It will make the intensity of the winter worse, colder. It will make the intensity of the summer worse, hotter. It will make both of those things change along the way. We are seeing sea levels rise over the past 100 years or so. 20 centimeters, we're not talking like yards and yards. And we're certainly not talking about 100 feet or 200 feet or anything like that. But considering we've got 500 million people on this planet who live at sea level, by the time we've got 50 centimeters there, we're talking 1.5 feet. What happens to all those people who now have to get up and leave where they've been living 1.5 feet underwater? Also, when our summers are hotter and when our winters are colder, that affects food production, and that can also affect the availability of fresh water. Believe it or not, most of the fresh water that comes for most people on this planet come from glaciers and ice caps on mountains and other kinds of things like that that get less and less when we get hotter and hotter. So that becomes an issue along the way. So yes, there is climate change. Yes, there is cause to be concerned. Yes, we are on a warming trend right now. Yes, we can do something about it because yes, we've done things about it before. No, we should not be alarmed that the world is going to end tomorrow, at least not from climate change. Yes, we should be making efforts to make sure we don't make things worse for the planet than we otherwise would need to do. So I think of John McCain, who was the presidential contender against Barack Obama back in 2008. And one of the things that I thought was good about his campaign was that essentially he and Barack Obama both were in agreement that there is climate change and we can do something about it. Because we've done things about things before that have turned out to be pretty good. If we change the way we generate power, if we change the way we manufacture products, if we change the way we sort of misuse things on our planet, because so many things that we do right now are limited in supply. Solar energy is not limited. Wind energy is not limited. Geothermal power is not really limited. Fossil fuels are limited. We're going to run out of those. Probably not in your lifetime, definitely not in my lifetime, but a couple of generations from now, shouldn't we be making the world a better place for our kids and grandkids? That's what John McCain said. That's what Barack Obama said. That's what Mitt Romney said. That's what lots of people on both sides of the political spectrum have said along the way. And that's what I believe as well. So make the world a better place for generations to come. And with that note, I will leave you until chapter 11.